Okay, so why do astronomical objects shine? And I put a few examples of astronomical objects on this slide. I guess I've used kind of Astro 101 type language here. What I mean is, why do they create light? Why can we see them? And so there's sort of three categories here of light creation that I'm illustrating. I'm going to do ask the class. Who remembers or would like to talk about why the moon shines? Why is the moon bright at night?
The sun is shining on it?
Yeah, the sun is shining on it and it reflects light. Wasn't a trick question. Reflection of light. So it's mostly, it's light from the sun that you're seeing when you look at the moon, reflected off the moon's surface. And the same largely, certainly in optical, with all the other planets. So you see planets because of reflected light. What about the sun though? What creates the light? Why does the sun shine, as they say? Fusion, yeah, that's what creates the energy. Do you remember where the light comes from though, Jesse?
It's black body emission mostly from
right.
the high temperature stellar.
So it's radiation, right? But specifically, it's thermal radiation or black body. Okay, very good. And the thing that makes the sun hot is the fusion. How about my final column? Why do these things shine? These are emission lines. So there's some source of energy that's heating up a low density gas and creating emission lines, causing the atoms to create emission lines. I thought we'd go through each of the physical mechanisms just very briefly. Also, a quick reminder of the electromagnetic spectrum. So obviously at Strawbridge, the optical telescope, we're focusing on the optical part of the spectrum. We will have a project where we discuss radio waves, but I will try to kind of bring in the other regimes of the electromagnetic spectrum. Astronomers use all of these regimes to study the universe. And I'll sort of try to mention what we see in particular in certain regimes. And then just a reminder of the sort of equations that are useful, right? The energy of light is the Planck constant times its frequency. So higher frequency light has a higher energy. And also this relationship between the speed of light and the frequency of light and the wavelength of the light. So longer wavelength is lower frequency and vice versa, since the speed of light is a constant. Hopefully all of that is just a quick review. Okay. And a reminder also about luminosity and flux. So luminosity is going to be the total energy emitted by an object. So this is actually has units of energy per second, right? And then the flux is what we detect, basically. It's the energy per second per unit area. And so the further you are away from the source, the lower the flux is, but the luminosity will always be the same. And then this one comes up a lot, right? That the flux is the luminosity divided by 4 pi r squared, where r is the distance to the source. And that's just the surface area of a sphere around the source with that radius. Surface area of a sphere is 4 pi r squared. But of course, as we're astronomers, we don't like SI units. Apparently that's not true. That's just really not true. But we still use magnitudes, hurrah. And so this was, as we've talked about, this was a system set up by Hipparchus, an ancient Greek, ranking stars by brightest to dimmest that they could see. And so you can see magnitudes 1 to about 6 or 7 with the naked eye. And then Norman Pogson, thanks to him, he proposed this mathematical formula for the magnitude scale. That means we can continue to use it. So the difference between two magnitudes is minus 2.5 times the log of the ratio of their luminosities or fluxes if they're at the same distance. All right, so the sun and all stars they shine because they're hot. Every object that has a temperature creates this black body radiation. Most of you have either taken StatMech or are currently taking StatMech, I believe. And so one of the things you may well do in StatMech or have done is derive the functional form of the Planck function, right, for the shape of the black body spectrum. So if you look at this graph, this is showing it in terms of wavelength. It looks similar-ish in frequency, but has slight differences. It just kind of has this hump shape. For astronomy in particular, remembering that the peak of the black body radiation is proportional to 1 over the temperature, and here is the actual equation, so the Wien's law. So the wavelength of the peak is 2.89, well, how many significant figures? 2.9 times 10 to the minus 3 meters Kelvin divided by temperature in Kelvin. So the hotter an object is, the shorter wavelength of the peak of its emission is at. And this is my favorite demonstration of that, which is a red hot bar of iron from a forge. In fact, you can see it's kind of white hot right at the end, and it goes through kind of orange through to red through to not really being totally visible. And so you can see, this is the black body radiation you're seeing, and you can see the temperature of it cooling off. You can see that the color of it changes. And so just a few more kind of example black body spectra. So the surface of the sun, 6,000 degrees Kelvin. It's obviously not a coincidence that the peak of its black body spectrum is the middle of the optical range, because of course we evolved to see on Earth. So our eyes have evolved to be sensitive to the light that the sun emits. Always makes me surprised though to think about the fact that a light bulb, a tungsten light bulb, must have a similar temperature to the surface of the sun. They're a bit cooler, but anyway, red hot objects, you'll often hear, infrared talked about as if it were thermal radiation, because, the black body radiation that people or room temperature makes peaks in the infrared part of the spectrum. Red hot objects also kind of peak in the infrared, but they look red because we don't see infrared. Similarly, the Earth's surface. And then, much cooler objects might have the peak of their black body spectrum in the microwave or radio part of the spectrum. So an example of that is the cosmic microwave background radiation, which is very cold and peaks in the microwave. And the converse, very, very hot objects like the surface of a neutron star, the peak of their black body radiation will be in X-ray. And my favorite star system, I think I've probably mentioned this to a few of you before, but there's a pair of stars in the Cygnus constellation called Albireo. It's the nose of the Cygnus constellation, and if you look at it with a telescope, you'll see there's actually a binary stars. There's 2 stars there, not just one, and you should be able to see the difference in color with the naked eye. So we don't have an eyepiece on the 16-inch right now, but if you get a chance to use the 12-inch and look at Albireo, you should be able to actually physically see this. And if you took an image through different filters of Albireo, we should be able to tell that they have different colors because they're different temperatures. Okay, so coming back to filters, right? Black body radiation, this is very broad band radiation, but stars have different colors because they have different temperatures. So if you're looking at something that's composed largely of stars, or that has stars in it, like a star cluster or a galaxy, those broadband filters should help you pick out the different colors that you can see in stars. And similarly, planets and the moon are just reflecting sunlight. So you want broadband filters in order to try to pick out the the temperature range. The set of filters we have, it spans the optical range. So you want one from sort of the blue side, one in the middle, and one at the red side. We sort of talked about how there's 2 different systems. There's the capital letters and the lowercase letters are 2 different systems. So you'll tend to find people stick with one system or another, and we don't have 3 of the capital letter ones. So you can't quite do that if you want a capital letter one in. You could do GRI, which is a very standard set of imaging that astronomers use, lowercase g, lowercase r, lowercase I. But there's no reason why BV, capital B, capital V, lowercase r, that's a good set of choices as well that span optical and should pick out these different colors. Okay, so we don't have a spectroscope on the telescope, but we do have emission line filters that pick out just the wavelength of specific emission lines. So I'm hoping this is all a review, just a reminder of the kind of spectra you might get if we did have a spectroscope. right? We talked about black body spectrum. It's very broad, smooth, this sort of continuous spectrum, like the rainbow that you see from the sun. It just looks continuous. If your hot, dense energy source is illuminating a low density of cloud of gas, but you're not looking like through the gas cloud at the hot thing, it's just illuminating it, and then you're looking at it kind of off to the side, this will have been heated up and then will emit, the emission line photons will go off in all directions. So even off to the side, you'll see the emission line, but you won't see the continuous spectrum in the background. So we see this kind of emission line spectrum from gas clouds and nebulae, like planetary nebulae, star formation nebulae, and galaxies with star formation clouds in. We'll see these emission line spectra. And then you also sometimes see absorption line spectra. So this is when you have a hot, dense energy source, which is then coated with the cooler density gas. The classic example here is the absorption lines that you see from the atmospheres of stars. So stars have an atmosphere. And so actually stellar spectra do have these absorption features in them if we were to do that. But that's an absence of light. So it's this kind of hot, low density gas clouds that are heated up by something that are going to look interesting in the narrowband filters, in the emission line filters. Okay, so which filters do we have? We have H-alpha filter. So here is a reminder of what H-alpha is. This is the Bohr model of hydrogen, right? And so it can have, it's got a single proton and then one electron going around it. Those of you who've done quantum mechanics, did you solve the Bohr model? Did you solve for the energy separations in quantum mechanics? Some nods. Yeah, it's the simplest atom, right? So it's, a thumbs up, excellent, thank you. It's the simplest atom, so it's often set as kind of the thing to solve. You solve for the energy levels. I'm not going to worry about doing that in astrophysics, but just kind of to talk about it again. It's such a common atom and so easy to solve that the different series, basically, of electrons dropping down in the energy shells and releasing electrons have different names. So you have the Lyman series, which goes down to the ground state, the Balmer series going down to the first excited state, and the Paschen series going to the third excited state. So it turns out it's the Balmer series, which is in the optical part of the spectrum. The Lyman series is UV and the Paschen series is in the infrared. Astronomers detect these as well, particularly Lyman alpha is in the UV, but if you observe that in the distant universe, because of redshifting, it gets redshifted into the optical. But here in the local universe, bright stuff that we can see with a 16-inch telescope in the suburbs of Philadelphia, it's hydrogen alpha is what we see. And this is going from the second excited state to the first excited state of hydrogen. So it's ionized hydrogen. And the thing that ionizes hydrogen are hot young stars, mostly, or in some cases, you get it from planetary nebula as well. So, the white dwarf at the center of a planetary nebula can be ionizing the hydrogen. And it's sort of a red line. It's at 656 nanometers, which is right in the red part of the spectrum. So in sort of false color images, you'll often see it coded red or pink. We have an oxygen 3 in square brackets filter. So what is that all about? So oxygen 3 is doubly ionized oxygen. So it's an oxygen atom that's missing 2 electrons. It's a old-fashioned chemistry notation that astronomers still use. And the square brackets mean that this is a forbidden line. I don't want to go into details of what forbidden lines are, but you see them in astronomy because the densities are so low. So you won't see them in a laboratory cloud of ionized hydrogen, if there is such a thing, because you can never get the density low enough to allow it. They have very low transition rates, right? So you need nothing else to happen to the atom before it has chance to do this emission. I put an energy diagram here that I got from Wikipedia. And I have to admit, I don't know what all the labels mean, so that was confusing me, and I was going to look it up, and I didn't get around to it. All right. Well, anyway, so I'm illustrating that you don't need to know all the details necessary, but it's an emission line that's cool, that's created by ionized oxygen. These, in fact, it's two emission lines, but both of them they're close enough together that they're both going to be in our narrowband filter. And again, it's ionized gas. It has a slightly higher ionization. You need slightly more energy to ionize oxygen than hydrogen, but actually not a ton more. They're pretty tend to coexist pretty well, but you will sometimes see like little variations. So I think this is the bubble nebulae. I took picked out a picture of it where they've put H alpha in red and oxygen 3 in green, and you can see that they're in slightly different places in the nebulosity. This oxygen 3 line, actually, this was news to me, but it's kind of cool. It was first detected in the 1860s, and they didn't realize it was oxygen because this is a forbidden line. It's not supposed to happen. So they initially called it nebulium. They thought they'd found a new element in these nebulae that was creating this line. And then it was a little bit later that people realized it was coming from this forbidden line of oxygen. So again, nebulae are good here. H alpha, hydrogen is much more abundant than oxygen. So the H alpha line is going to be more luminous, more flux than oxygen. So faint stuff, I would stick with H alpha. I'm not convinced galaxies will be able to see much hydrogen alpha emission in a galaxy from our telescope, but maybe we can. We haven't tried yet. But if we can't see H alpha, we're definitely not going to be able to see the other two lines. So, but for like planetary nebulae, star formation nebulae, this should be beautiful. And then the final one we have, I knew much less about. S2 is singly ionized sulfur. That much I could work out. It's another forbidden line. It's at 670 nanometers. It's another low density ionized gas stuff, so nebulae can be interesting. Here is NGC 6888. Excuse me, actually an image from an amateur. So there are, like we are, I guess, our 16-inch telescope here, right? It's not really a professional telescope. We're not going to do too much research probably from this telescope, but there are amateurs who just for fun do astrophotography and will have emission line filters. And so this person is playing with how this object looks in the different sets of colors and filter combinations. So I just wanted to mention emission lines in other parts of the spectrum. I am contractually obliged to mention the 21 centimeter line. That's not true. This is a spin flip line from the ground state of hydrogen. It's what a lot of my research is based on, and that's a picture of the Green Bank telescope. The 21 centimeter line, again, it's another forbidden line. You don't see it in the laboratory, but low densities in space mean this is a very frequent line that we observe in the radio part of the spectrum. And there are other radio lines, there's all kinds of slews of different types of lines. I wanted to mention just briefly molecular lines in case that comes up. So you're very familiar, I'm sure, with the idea that you have these energy levels, discrete quantized energy levels in atoms. What's a little harder, I always found it a little harder to get my head around, was the idea that molecules and vibrational and rotational modes of molecules would also be quantized in energy levels. And so you have these quantized energy levels associated with the angular momentum or vibrational energy. So simple harmonic oscillation you can use to model it, believe it or not. They actually have quantized lines associated with them. The carbon monoxide lines, CO lines, are really commonly used in astronomy. One of the reasons actually is that carbon monoxide tends to coexist with molecular hydrogen. Molecular hydrogen is completely symmetric, so it doesn't create any significant amounts of these rotational or vibrational lines. But there's lots of people sort of calibrate the relationship between carbon monoxide and molecular hydrogen and use the amount of carbon monoxide to trace molecular hydrogen. And then, so this is a picture of the ALMA observatory, which is the one that was used to detect the molecule in the atmosphere of Venus, but it can also detect carbon monoxide in distant galaxies, or in this example, these are protoplanetary disks. And I think this is a combination of molecular lines, but also the thermal radiation in them, but they're quite cold. So their thermal radiation is in the sub-millimeter part of the spectrum. that ALMA is sensitive to. We put it in the high desert in the Atacama because this molecule also creates lines. This is water, right? So there's all kinds of molecular lines caused by water in our atmosphere. And so you want to get above as much of that as possible to do submillimeter and even some infrared observing. Right, and then I wanted just to mention, since this is the upper level class, there are other ways of creating light. You'll hear about non-thermal sources, particularly those of you who've been studying pulsars will have heard about non-thermal sources. Probably in upper level E&M, you might have learned about bremsstrahlung, braking radiation, or synchrotron and cyclotron also. Basically, anytime an electron accelerates, you're going to have energy absorbed or emitted. Usually in the form of a photon. So bremsstrahlung here, we have an electron coming along and it interacts with this proton and it changes direction and you emit a photon. If you have cyclotron, that's electrons going around a magnetic field slowly, or synchrotron is relativistic electrons going around a magnetic field. And do you remember they're going to curl around it, right? They make a little helix shape because of the direction of the forces, the EM forces. So we see this in astronomy, we detect this, particularly in the radio part of the spectrum, but also these types of emission also create emission in X-ray. One of the reasons it's particularly seen in radio is that this is our thermal radiation curve, our black body curve, and it drops off at long wavelengths, whereas non-thermal radiation, the synchrotron, cyclotron, tends to have this just increasing intensity with wavelength type of spectrum. That's something you can actually calculate what that spectrum should be in E&M. I remember doing it at some point, but don't ask me to do it today. I'll look it up for you if you want to do that. And this is an example of an image where this is a synchrotron emission from the Crab Nebula. Well, I guess it's from the pulsar thing in the center of the Crab Nebula, but you can actually see right down here in the center is a neutron star, and this is an accretion disk around it and some jets, and this is a model of what synchrotron emission should look like from that nebulae, and they indeed look somewhat similar. Oh yes, and then finally, I didn't want to leave out LEDs. This was actually inspired by Sadie Kenyon-Dean's thesis last year. Lots of the artificial lights that you'll see on campus are LEDs. So these are not creating light by any of these mechanisms. Instead, they have a certain type of electronic circuit in them where you end up with electrons changing energy between a conduction band and a valence band, and that change of energy creates light. And so that's what light emitting diodes create light by this mechanism, and can be incredibly bright, as you will discover if you try to observe late at night.